This is a problem for a power transistor, and these are the parameters that are given. TJ max is given as 120 degrees C. PD max is given at 2 watts at a case temperature TC of 25 degrees C. The thermal resistance theta, which means the thermal resistance between the junction and the case, is 50 degrees C per watts. This is the thermal resistance between the junction and the ambient, which is 100 degrees C per watt. So this is the overview of an actual circuit. So we have a die in the center of a case. This would be where our junction temperature would be located, right at the die itself. Between the die and the outside of the case, there's a thermal resistance. This is between the junction and the case, so it would be labeled JC. So this is the thermal resistance of 50 degrees C per watt. After you have a case, you can put a heat sink on it, which I've labeled here as the red. That would be then a resistance between the case and the outside of the sink, so I would label that theta CS. Then once you reach the outside of the sink, you have again a thermal resistance, which is not seen this time, but which goes from the sink itself outside of it to the ambient air. And so the ambient temperature in the room. So this would be SA is the notations for those. So drawing this in a circuit diagram, which we're more familiar with, PD is the power dissipated. That is modeled as a current source. The top here would be your junction at your actual die location itself. This is going to be the junction between J and your case, so the junction itself and the case. This then would be your location at the end of the case. Then just like here, it would be theta CS in this case, so C, the case to the sink. This will be your sink. Once you reach the sink, then the outside of that will be to the ambient. So this will be sink to your ambient. So in a lot of cases, sometimes you won't have some of these here. So you can have from the junction itself right to the ambient and neglect all of the effects of a case. And if you don't have a heat sink on there, then it would be just the neglecting of the case itself. And so neglecting all of those, these can all be lumped up into one, which would be theta between your junction and your ambient. You can also not have a sink. In that case, you would have a thermal resistance just from the case to the ambient, theta CA. So once you know several pieces of information, you can actually find more information out. So in the question, we want to find out what is the maximum ambient temperature, so the max TA, to ensure safe operation at a power dissipation of 0.2 watts. So we go back to this, we know this information here, these are always, thermal resistances are fixed values. So this is 50 degrees C per watt. We also know the overall combination of all of them is going to be 100 degrees C per watt. So we want to know the max TA, which is going to be here. So to find that, we know JA, so we know the total between them. We know the max condition for TJ max at 120 degrees, so we could find it at the specific PD. So TJ minus TA, so we treat these as voltages. So TJ minus TA would be your voltage drop is equal to your current times the resistance. So in this case, we're going to solve TA. So that's going to give us 120 degrees minus 0.2 times 100 degrees C per watt. So this gives us a max ambient temperature of 100 degrees C for these conditions. Another question is, what is the junction temperature when the transistor dissipates 500 milliwatts? So the dissipation in that one would be 500 milliwatts. We want to know the junction temperature, TJ, when the case temperature is also 30 degrees C. So that would be, we know this information, we'd have this fixed value, so in this case we just want to find TJ. So TJ would be equal to, or I can do the drop first, TJ minus TC is equal to PD theta JC. So TJ is equal to 30 plus the 500 milli times 50 degrees C per watt. So that gives a temperature at the junction of 55 degrees C.